Soluble. So Daniel cell, sorry, in the Daniel cell, you see that there are two chambers. In one chamber, left hand side chamber, there is a zinc rod immersed in an aqueous solution of zinc sulfate, whereas in right side, copper wire is dipped in aqueous copper sulfate solution. And if these two rods are connected externally and connected to a bulb, then the bulb will glow, right? And it is a reversible cell. Now there is another kind of electrolytic cell. You know, I think you can easily distinguish between this electrochemical cell and electrolytic cell. In electrochemical cells, what happens? We have the two solutions, separate solutions and two separate electrodes. And when these are connected externally, then at the expense of chemical reactions occurring within the cell, electricity is produced. Whereas in electrolytic cell, what happens? Electrolysis occurs. Why? When current flow to the solution. So electrolytic cell, electrolysis occurs when we pass when we pass electricity uh, through the solution taken in the electrolytic cell, electrolysis will occur. So electricity flows through the uh, reactions and the respective vector. Okay. So electrolytic cell and electrochemical cell, we know the difference. And now we are interested in this electrochemical cell, which is a reversible cell. Reversible means chemical reactions occurring in the cell produces electricity. And why it is reversible cell, that I'll discuss. That this is the Daniel cell, and it is written in compact form like this. Say there are two vertical lines are there. I see this represents basically salt bridge. The purpose of using the salt bridge is it connects the left and right side electrodes. Nothing else. This is the rule. Okay. So in the left hand side, you see the zinc electrode is immersed in an aqueous solution of zinc ion, and it is represented like this. Zinc metal, a vertical line is there, which is separated from the zinc plus 2 aqueous solution. Likewise, in the right hand side chamber, you see cupric ion coming from this soluble salts of copper salt, maybe say copper sulfate here, and it is separated by a single vertical line with the copper metal. And left hand side chamber we call anode chamber, and right hand side chamber we call the cathode chamber. So basically there are two half cells, zinc ion and cupric ion and copper. These two are separated. These two are separate uh, electrodes. Left hand uh, electrode we call anode chamber and right hand we call cathode chamber. Why we call this cathode anode chamber or cathode chamber? Because anode means oxidations. Actually, in the left hand side, this half cell, right? This half cell reaction is represented like this. Wherein zinc, that is zinc metal, passes to the aqueous solution as zinc plus two ions, leaving two electrons that would be deposited on the electrode itself, that is on the zinc rod. Likewise, in the right hand side, aqueous solution, copper ion from the aqueous solution will collect two electrons from the electrode that is copper metal, and it will be converted or deposited on the at the copper on the copper atom of the electrode copper metal. So what would happen if you connect these two cells, half cells, then chemical reactions occurs, and as a result of chemical reactions, what should be the apparent changes that one can note or one can see that zinc rod will gradually decay because zinc metals passes to the aqueous phase as zinc ion, whereas copper ions in the right hand side chamber or half cell you see cupric ion deposits on the copper electrode. So that means left hand side or the anode will be gradually age, weight will be lost, whereas due to accumulation of copper metal on the right hand copper metal, the right hand side electrodes, that is cathode, will be heavier. Right, weight will increase. So in the left hand side electrode will be decay, whereas right hand side electrode will increase, grow. Okay, and these are the two half cell reactions. And if you add these two equations, then what would happen? That is called overall cell reactions. Just algebraically, if you add these two equations, you see that the electron balance should be made so that they are cancelled out and we are left with the overall cell reactions, that is Zn plus C plus 2 equal to Zn plus 2 plus 3. Basically, this is nothing but an redox reaction, that is oxidation uh, reactions, where zinc ion is oxidized itself, whereas cupric ion present in the solution is reduced to metallic copper. And this is the overall cell reactions. Okay, and this is shown in the schematically like this. Now, why this cell we call a reversible cell? Daniel cell is popularly is called a unique reversible cell because now instead of connecting the two electrodes externally, if we allow electricity to flow into the solution, say after a certain amount of electrical after certain reactions, right? Then what would happen? Then what would happen? Suppose if you allow to flow current in the opposite direction, then you see whatever amount of copper metal deposited on the plate that will pass into the solution as the plus ions, whereas the zinc rod or zinc plate which has been decayed, which is decayed partly, that zinc ion again coming from the solution phase will deposit on the decayed plate. So that means if you allow electricity in a reverse direction, then the electrodes which was decayed now it will be uh, grow in size in its initial stage, whereas copper electrode, where copper atoms deposited significantly, those copper deposited copper metals again pass to the cell. So that means the solution along with the electrodes will be restored again, right? If current is flowed in a reverse direction to this Daniel cell. Okay, so that's why Daniel cell is a typical example of a reversible cell. Now let us consider another cell written like this: ZnH2SO4 C8. It implies that H2SO4 being a common electrolyte, we can take, we can merge two electrodes, zinc rod and copper rod, in this aqueous H2SO4 solution. And what would happen? Interesting that if you connect externally these two electrodes, that is copper and zinc, that we call electrochemical cell, these are the reactions that I have shown. That is zinc ion as usual passes to these zinc ions, with liberation of two electrons, whereas H plus ions taking two electrons is eliminated as H2 gas in the right hand side. Okay, so that means hydrogen will evolve on the right hand side, whereas right across the along the electrode surface, whereas zinc rod will gradually decay. Now, if we pass when electricity is passed through the cell in the opposite direction, then what will happen? Just like Daniel said here, again the reverse reaction should occur, but interestingly see, not exactly reverse reactions occur. What happens? Copper will goes to Cu plus 2 plus 2. That means copper electrode will decay and zinc electrode will of course be uh, which was decayed that will be again filled up. So zinc electrode will be restored, but copper electrode will not be restored because initially when it was taken as a electrochemical cell, hydrogen evolves, right? So the concentration of hydrogen ions in the solution will decrease. And those hydrogen ions which goes from the solution due to excess sulfate ion, copper metal ionizes to C plus 2 to neutralize the solution. So basically, this is the reactions that would occur. So whatever hydrogen ions after getting two electrons removed from the system exactly to balance this excess negative charge in the solution due to presence of sulfate ion that is counterbalanced by the copper ion coming from the copper electron. And so you see these two reactions are different, right? So that's why the concentration of the solution will change, right? That is concentration of H2SO4 will decrease, right? At the same time, the concentration of copper sulfate in the solution will increase when the reverse uh, current is poured through the solution, in the reverse solution. Okay, so this is the example of two reversible and irreversible cells, and okay, now these are the actually interesting part that okay. Now actually in electrochemical cell, how electricity is produced or how electrical energy is obtained. You know, from the energy conservation, the certain amount of energy must be converted into this electrical energy. Now, what is the source of how this energy could be produced at the expense of which kind of energy? Actually, it is the Gibbs free energy that comes from the electrochemical reactions will produce the electric energy. So in electrochemical cell, like Daniel said, you see that this is the fundamental reactions that is delta G negative delta G that is gives free energy change arising from chemical reactions that must be equal to the electric energy given by NF into E, where capital E represents the cell EMF, capital F denotes Faraday of electricity, which is constant, and its values is generally taken as 1 Faraday equal to what? Can you remember? What is 1 Faraday? It is equal
nine
to
nine six five
1
double
to
zero.
right. For calculation purpose, we generally take 965 Coulomb. Okay. And N denotes actually number of how many electrons are transferred in a stoichiometric presentation. Say for example, copper electrode, you see for electrochemical cells, these two electrons are produced, so two electrons are exchanged, so n equal to 2. Now gives Helmholtz equation if we use, then delta G equal to delta H plus. Thermodynamically, it can be shown that these quantities are like this. Okay. So this you can find, all these things you can find clearly in this book, PC Roxy textbook. Uh, physical. This is available, I think, most of you, or you can find it from a library. So I am not discussing all these things because these are not relevant for you right now. Okay. But only thing you have to remember, this quantity, that is Nernst equation that we will discuss. Okay. What is Nernst equation? That I can show you. You are familiar with this, but I can show you what is that. Actually, this is a arbitrary chemical reactions taking place in a electrochemical cell where small a, small b, small c, small d refers to the stoichiometric balanced coefficients, and capital A, B are reactant species, maybe ions, neutral molecules, and capital C and capital D denotes the products. And this, for this reaction, there is an equation thermodynamically one can write that we call reaction isotherm. So what is reaction isotherm? I am not, this expression can be derived from thermodynamic consideration, but it is not included in your syllabus. So we can write delta G equal to minus RT ln log E base. Ln means natural logarithm Kc, where Kc denotes uh, equilibrium constant in concentration scale in terms of concentration, and capital T is the temperature in Kelvin, R is a gas constant, plus RTLN, this part. If you look at normally what we write, equilibrium constant we generally express like this, that is concentration of product C raised to the power C, D raised to the power, exponent comes from this balanced stoichiometric coefficients, right? Now this part, that is the quantity within the parenthesis, these concentrations do not represent the equilibrium values, right? So we can write it in compact form, delta G equal to minus RTLN Kc plus RTLN QC. Now QC denotes all these quantities within the parenthesis denoted by QC, capital QC, what we call proper reaction quotient. QC we call, it is called proper reaction quotient. QUOTIENT, proper reaction quotient. QUOTIENT. Okay. So this QC is called proper reaction quotient, and this expression that is within this whole bracket, that is delta G equal to minus RT ln Kc plus RT ln Qc. This equation is popularly called reaction isotherm. Now, at equilibrium, the free energy change at a given temperature and pressure is equal to 0. That we know. So, if we consider the reaction at equilibrium, then what would happen? Whenever you are putting delta G equal to 0, that means these concentrations C, D, A, B within this parenthesis should be should be represented as equilibrium concentrations, right? Because at equilibrium delta G equal to 0. And uh, if delta G equal to 0, then basically from these expressions one can easily draw a conclusion that proper reaction quotient basically identical to the equilibrium constant in concentration scale. Why it is true? Only this is true when the reaction attains an equilibrium state. Okay, because delta G would be equal to 0, and one can write on comparing that reaction quotient would be equal to this. Okay, now delta G we generally represent minus RT ln Kc. This quantity we call what we call delta G 0, right? You know these expressions that delta G 0 superscript stands for what? Delta G 0 basically uh, delta G 0 indicates that at a given pressure, say normal atmospheric pressure and 298 Kelvin temperature, right? Of course, the pressure is 1 atm or 1 bar as per convention, and it is basically a function of temperature. Delta G 0 does not indicate that the temperature is 298 Kelvin. Rather, it is 0 superscript indicates the value at P equal to 1 bar, right? And temperature may be anything, not 298 Kelvin. Okay. So basically like this. And so since delta G 0 equal to minus RT ln Kc, then what we can write? We can write it in compact form that reaction isotherm can be represented like this. Clear? Now, do you have any confusion? Please let me clarify. Because the original expressions, that is reaction isotherm, that I have written in this form, right? Okay. And this is the another expression of the reaction isotherm, Gibbs reaction isotherm. And E0 denotes what? Standard EMF of the cell. So, as you know in our earlier discussion, that delta G equal to minus NFU, and delta G 0 equal to, it would be minus NFE 0. Okay. So delta G equal to minus NFE and delta G 0 equal to minus NFE 0. So we have written like that, that is minus NFE equal to minus NFE 0 plus RT ln QC. And if you just simplify, that is E equal to 0, then you can write minus RT by NF ln QC like that. Okay. And QC is reaction quotient. Proper reaction quotient is given by these expressions. And so this equation is famous Nernst equation, right? This is the Nernst equation, this expression. So this is very, very, very important to calculate the cell EMF E, where E we call normal cell EMF and E0 we call standard cell EMF. Now standard cell EMF can be calculated from the respective half cells. Okay, that I can show later. Okay, and this equation that we know, this can also be represented like this. So this is also very important. Now in the Nernst equation, whether this one or general expression, this one, what about the magnitude of this constant term that you should know? Actually, say from these expressions here, R is the universal gas constant. First of all, you express Ln in terms of natural logarithm log E base, we replace by log 10 base. So we multiply this factor 2.303 RT by NF log 10 base case. Now, if you write down the more explicitly this constant, then we can write 2.303 into magnitude of R is 8.314 in terms of Joule into temperature T is 298 Kelvin and N into F is the Faraday 96520 in Coulomb. Now there is an expression, that volt into Coulomb that gives rise to the energy, right? So that's why Joule by Coulomb, J by C would be equal to what? Right hand side in potential V, right? So that's why, and this constant factor 2.303 into 8.314 by 96520 into 298, these whole factors, right, is coming out to be 0.059 by 10. So unless temperature is not mentioned, we have to consider temperature 298 Kelvin. And if you have a calculator, you can check that E0 can be written in this compact form, that is 0.059 by N, where N is the number of electron transfer takes place in the reactions. Okay, in the half cell reactions or in the total cell reactions. Okay, and E equal to general expressions E0 minus the same constant we can write like this minus 0.059 by 1 like this. And I have shown to apply, I have given here an application of this Nernst equation for a Daniell cell, where a Daniell cell as before is represented in compact form like this. Okay, that is zinc ion separated by the electrode of another half cell electrode, that is copper ion. And so we can write, as we discussed there, what is how to calculate standard cell. Standard cell image is 0 equal to this one. Okay. Okay. Now at this stage, if you have any question, okay. 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 So in the Daniell cell, standard cell image equal to the convention is oxidation potential. I generally used to write down this form, that is zinc to Zn plus 4, whereas E0 in the right hand side reduction potential, one has to write like this. Sometimes, what is the relation between these two? reduction potential, as you know, that the reduction potential uh, can be written as oxidation potential, and only thing is that negative sign will appear. So instead of E0 Cu plus 2 to Cu, we have to write minus E0 Cu to Cu plus 2. So this is the convention so that you can easily identify. Suppose if you are asked to calculate standard cell EMF from the given half cell reactions, right? Half cell EMFs are given. If both are given, say, oxidation potential or both are given reduction potential, so accordingly you have to take care about the sign change that you have to do. Otherwise, you get an erroneous conclusion or result. Okay, so that's why I have written here. This is the standard practice. If you find an oxidation potential, if it is positive, and if you put its negative value, then that would indicate the reduction potential. Say, for example, zinc when passes to zinc ion, that we call oxidation potential, whereas the reverse case, that is zinc plus 2 to zinc, this represents a reduction process, and that's why this electrode potential that is represented like this is called reduction potential. Okay. Okay. Likewise, but a general cell EMF can be represented as a sum of two half cell potentials, which are not standard, of course. Now, for a practice, this sort of problems, numerical problems, you can expect in your final semester exam. So, you have to practice regarding how to write down the half cell reactions of a given cell. Suppose a cell is given to you, then you have to write down the how to write down the half cell reactions, and then how you can apply Nernst equation for each half cell reactions. Okay, and how to find the ultimately you have to find out or write down the Nernst equation of the cell. How to write the cell reactions for a given cell. How to construct cell for a given half cell reaction. So these things you should know. Okay, how to construct a cell for a given half cell reaction. Sometimes a cell reaction is given to you, and you are asked to construct the for this PC rocket textbook numerical problems are there, so you can proceed for that. So this is very important. How to write or construct the cell from a given reactions. That practice you have to do that, solve this kind of problems. And what are the types of single electrodes that we should know? That I'll discuss in short. Just what are the different types of electrodes? It is given in this book or in the net you can find. Silver, these metal ion electrodes. I have given one example. The silver passes to silver ion plus electron. It is represented like this. Silver, yeah, or vertical line, silver plus. Likewise, a gaseous electrode, a typical example is this. Platinum. Platinum Pt in bracket wants to write Cl minus plus Cl2. This indicates these reactions, that is chloride and converted to chlorine with liberation of two electrons. So if you write down this gas phase gas electrodes, so basically this we call a gas electrode. There may be hydrogen electrode or like that. So all these things you can write like this. But this gas electrode represents what is that? Oxidation. if you write down the gas cell, this reaction, say PtCl2 to Cl minus, then this electrode potential, this represents a reduction because reduction occurs. Here oxidation occurs, the reverse reaction. For the reverse reactions, the electrode representation should be like this. PtCl2, this vertical line, Cl minus. Okay. Similarly, this is another electrode lead amalgam, right? Because amalgam, a lead metal, due to say strong activity, sometimes the activity could be reduced by amalgamation. Generally, sodium metal, lead, they can be amalgamated, and the reactions then would be small, right? Instead of vigorous. So that's why we represent like this. And this electrode generally represented like this. That is lead in bracket Hg, vertical line Pb plus P. That means lead ions is in equilibrium with this lead electrode. In presence of these lead ions will form the equilibrium. Now there is another second kind of electrode that we call metal sparingly soluble salt electrode. What is that? I've given two examples. How to represent the metal sparingly soluble salt electrode? There are two examples. You see, silver chloride in brackets solid, Hamadi KCl. Whereas mercurous chloride solid KCl. That means silver metal, right? That plate at the bottom plate, its surface is covered with solid silver chloride deposit, and this whole system is put in an aqueous solution of KCl. So that means that this is a metal here coating of silver chloride. Right, this coating is given. So this is silver and its plate is coated with silver chloride solid. And then this whole thing is immersed in an aqueous solution of potassium chloride, KCl solution. Okay, so this is called metal sparingly soluble salt electrode. Another example I have given mercury. Another example is this lead sulfate, potassium sulfate in aqueous. Okay. Now there is a question. Suppose this is the representation of a this cell, that is metal sparingly soluble cell, and if we write down this, then what should be the cell reactions? It is given by this. For this particular hub cell, this is a hub cell. For this hub cell, these are the reactions taking place. Right? You see, silver in bracket is denotes metallic silver. It passes in the aqueous phase silver ion with liberation of one electron. This silver ion is combined with the available chloride ion present in the aqueous medium to trap as silver chloride, and this silver chloride solid deposit on the silver metal surface. So the total half cell reaction is given by this one, and this denotes oxidation, right? Silver plus Cl minus silver chloride, because electron is liberating. So that's why this is a representation which denotes oxidation. So this is one typical example how to write down the half cell reaction for metal currently soluble cell. For lead sulfate, you can do yourself like this. Now there is third type of electrodes, that is oxidation reduction electrodes. This is very important. Okay. Okay. আমার কিছু বলার নেই, আমি বলে দেবো supervise করার জন্য যার জন্য দরকার। So only 30 of you are present. I think you are not interested or you have any problems. I don't know. Uh, Maybe you have learned so many things already. Okay. So if you have any question or any, so in the next class I will discuss several numerical problems based on these discussions, today's discussions, right? And before that, I would like to conclude this part. That is, so you know this fourth type of electrodes, that is called oxidation reduction electrodes. The platinum metal rod is dipped in an aqueous solution of ferrous soluble salts of ferrocyan and ferricyan. Then this reaction should occur, right? Then this is the reactions that would occur. Okay, this is one example. Likewise, this represents oxidation, but and it should be represented like this. That is platinum in bracket Fe plus 2 to Fe plus 2. So this is oxidation, and sometimes it is written like that. The potential E standard partial potentials for this equal to E0 Fe plus 2 to Fe plus 3, and that will be equal to minus E0 Fe plus 3 to Fe plus 2. That is, first one is standard oxidation potential, and this is standard reduction potential. So if standard reduction potential is given, then you have to put a negative sign to get oxidation potential and vice versa. Like that. So this is another typical example where stannous and stannica and remains in equilibrium. And if you put a platinum metal dipped in the solution, it will be acting as a stannous-stannic oxidation, okay, reduction. So in this way, you can construct and you can get. Okay. So this we have, I think we have discussed almost all the things. Suppose there is an equation like this. So this is a given cell, yeah, cell, lead sulfate, that it is sulfate ion, copper, cupric and copper. write down the individual electrode reactions and the total cell reactions. How will you proceed? Right. In the salt bridge, you know potassium and chloride, and that is saturated solution of KCl. And that is the because the why potassium chloride salts are chosen. Sometimes ammonium nitrate are also chosen. Can you guess why
Sir,
potassium
small
chloride?
size, so high mobility.
No, actually potassium chloride, potassium and mobility of potassium ion and chloride ion are comparable. Right. So that's why in the salt bridge, this basically inverted U tube where the saturated solution of KCl and agar-agar or any starch materials are mixed together and form a semi-rigid solid. Okay, hot concentrated solution of a mixture containing saturated solution of KCl and starch. This is poured in the uh, cell in this tube, and then after cooling it is put in this inverted form where the materials within this tube forms a semi-rigid solid. The purpose of this solid bridge is to connect, make an electrical connection between the two hub cells. Okay. Now for this given problem where given cell is there and how to write down the individual hub cell reactions. Say for the present case, one has to write follow this method. This is one hub cell and this is another half cell reactions. And if we add together, this is the total cell reactions. Right. So electron balance should be carefully taken while writing the half cell reactions. This is very important. Okay. So this is total cell reactions for this present problem. Likewise, there is another cell. How to write down the cell reactions, half cell reactions that I have written it here. Total cell reactions. In the right hand side, we have a hydrogen electrode, a gas electrode, and in the left hand side, zinc electrode is there. Okay, so this is the upsell reactions and this is the total reactions. Now the reverse things. Suppose this is the reaction given. You have to design the electrochemical cell. That is another kind of problem that you can expect. And how will you proceed? Right? Given this cell reaction, you have to design a electrochemical cell. Now this is the so to proceed that you have to write down the identify the upcell reactions, the deoxidation part and reduction part like this. And once you write down the oxidation and reduction reactions with proper electron balance, then you can easily write down the two half cell reactions and construct the cell like this. At the present problem, it would be like this. Okay. So these are the examples I've shown where given a cell, how to write down the cell reactions and the vice versa. That is, given a cell reactions, how to construct or design an electrochemical cell that we have discussed. Okay. So these sorts of problems you can expect in your end-sem examination. So be carefully write down all these things. So, okay, in the next class, we'll do some numerical problems. I think that would be better for you to have a discussion. Okay, and if you have any doubts or any question, you can raise any questions, please. If you have any confusion, then you can raise any questions. Okay.
Thank you, sir.
I think it's all right. Okay, so in the next class, I'll discuss some numerical problems based on today's discussion, that is from electrochemical cells and conductances. I'll give some numerical problems and the problems that you can expect in the final semester examination. Okay, okay. Thank you all.
Hello, sir.
Yes,
Sir, you have not yet assigned us the lab
yes.
experiments.
Today night I'll create a classroom and will post this home assignment and also those laboratory assignments. Okay,
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 sir.
okay. Thank you.